channel. My name is Precious. Alright, so this is a continuation of our lessons on systems of linear equations. Remember that this is coming from our playlist on linear algebra. Okay, so we've been able to see the concept of vectors and algebra of vectors and all of that. And now we are currently on systems of equations. We've been able to define what a linear equation is as an equation of this form: a1x1 plus a2x2 plus up to an xn equal to b, where we said that your a's or ai's and your b are constants. That's any number, while your xi's or the x1, x2 up to xn are variables. Alright, so we also went further to see that systems of linear equations, remember here I only just neglected the linear equations. Everything we're discussing here are just linear equations. Alright, so for a system now is a combination of two or more linear equations. Okay, so if in that case we said that the general form is of this form: a11, a12, and then a1n, and then you now have a21x1, a22x2, and bm. Alright, so this is the general form of a system. It contains more than one equation. Alright, so in today's class we'll be looking at the concept of solving a system of linear equations, and these are the things we are going to see. So what is the meaning of solution of a system? What does it mean? What if we are asked to get the solution of a system, what exactly are you asked to do? Now we'll give examples and we will see what a consistent equation or consistent equations are. We'll see types of solutions, and then we'll now go into Gaussian elimination, which is the method of solving systems of equations, and then we'll see examples. Alright, so definition. What is a solution? So a particular list of scalars is considered to be a solution of a particular system. So let's assume we are referring to this system. Let me call it star. Okay, so we say that the values, or let's put it this way: x1, x2 up to xn is a solution of the system star. Is a solution of star if it satisfies all the equations of the system. If it satisfies your star. So if the numbers x1, that means if you are able to find the value of x1, x2 up to xn that will be true for all these equations, then we say that it is a solution of the whole system. Now remember that the single difference or the particular difference between solution of a system and that of a linear equation is that if I have a linear equation, let's say 2x is equal to 5 now, so then you are just looking for a solution, that's the value of x that will satisfy just this equation. But when it comes to a system, let's take it that this is maybe plus 3y equal to 1, and then you have another x minus, let's say, 4y equal to, let's say, 8. Okay, so in this case, you are not just looking for the value of x and y that will satisfy equation 1 or equation 2. It is possible to get a set of solutions that will satisfy equation 1 but will not satisfy equation 2. If that happens, then, for instance now, if I put my x as 2 here, and then put my y as -1. If I put my x as 2 and my y as -1, you will see that it will satisfy equation 1. Of course, 2 times 2 will be 4, 3 times -1 will be -3, and if you join the 2, you get 1. Then if you put the same values here, you will see that it will satisfy equation 2. So what is a solution for equation 1 may not be a solution for equation 2. But we are looking for the set of values of x and y that will satisfy 1 and at the same time satisfy equation 2. Those set of values are what we call the solution set of the system of equations. So if the system contains 3 equations, your solutions must satisfy both equation 1, 2, and 3. And whatever is in the solution set should be able to do that. Alright, so that is what we mean by solution of a system. And so we can take some examples now. Now look at this. For example, you look at this. If I have 6x1 minus 7x2 equals to negative 15, so and then the second equation, you can see clearly that of course we are going to solve, we're going to see how to do this. Is of course a simultaneous equation. It just has 2 variables. It's easy to do this simultaneously, but then we're going to see how to solve it using the Gaussian elimination. Now, but before then, just for us to see what a solution set is, if I put my x1 here as 1 and put my x2 as 3, you see that this will satisfy the system. So of course you can run a check. If you quickly run a check here, you will see if I put my x1 as 1 minus 7 by 3, of course this is 6 minus 21, that's correct, minus 15. And at the same time, for equation 2, this will be 5 times 3. Of course, this is 4 plus 15, which is also 19. So can you see that this satisfies both equation 1 and equation 2? Therefore, you can then say that 1, 3 is a solution. Is a solution of this system. Okay, so usually we will put it in a vector form. So this is a solution for this particular system. And you can get other solutions. And so a combination of all the possible solutions of a particular system is called a solution set. A solution set. So if we can collect all the possible solutions, of course, like we are going to see types of solutions, you will see that there are some systems that have more than one solution. For instance, this one, it is possible that if we solve this, you can get more than one solution. And if you have more than one solution, a collection of all the possible solutions is what we call a solution set. Alright, so having seen the definition and what examples of some solutions, then what is a consistent equation? Okay, so a consistent equation is an equation or a consistent system. It should actually be consistent system of equation. Of course, we also have consistent equation, which I defined in our previous lesson. So a consistent system is a system that has a solution. Like we are going to see other types of solutions, there are systems that don't have solutions, that it is not possible to get the values of x1, x2, no matter the number of x values, that will satisfy all the equations present. So you say that such systems are inconsistent. So such systems are inconsistent. You know, that's why, of course, in normal conversation, you can say someone is inconsistent. That means you're trying to solve the kind of person that person is, and you've not been able to do that. So you say the person is inconsistent. But when a person is consistent, that means the person has integrity. You can actually say what this person can do in this kind of situation. So the same is applicable in this case. So a system is said to be consistent if you can find solutions for it. But if it is not solvable, we say that it is what? Inconsistent. Alright, so quickly let's now look at types of solutions that can be seen, or what we call cases of some systems of equations. You can have a system of equation and you're solving. There are 3 major cases or 3 major types of things you will see in the end. And this we are teaching you to see it, that even from the beginning of your solving, at least to the point where you have reduced it to Gaussian elimination form, or sorry, what we call the echelon form, you should be able to determine at that point whether this system will have a solution or not. Okay, so now let's go. So the first one is the no solution case. So you have the no solution case. So a system may have no solution, and we are going to see, like I said already, this is said to be inconsistent. We are going to see the condition of a system that will show you whether it will have a solution or not. And then number two, if the system is now consistent, it can be of two types. So it is either it has what we call a unique solution, unique in the sense that it just has only one solution. Like what I said here, 1 and 3 is a solution. It is left for us to check when we start solving whether this is the only solution for this system. If it is the only solution, then you say that this system has a unique solution. That means it just has one solution that can satisfy it. And then thirdly, we now have what we call many solutions. And some books will say infinitely many. So a system can either have no solution, or may have a unique solution, or may have many solutions, or infinitely many. You recall that when we were at a younger or maybe a lower class level, you remember that when we were taught simultaneous equations, our teachers told us that if you are given something like, let's say, 2x plus y equal to, let me say, 10, they will tell you that it doesn't have a solution, okay, because there are two variables that you can't solve it. But of course, that's not true, and linear algebra will teach you that whenever an equation is of this form, that is more variables than the number of equations, it is easy to see that it is going to have many solutions. And of course, that is the condition for many solutions, which we are going to see as we continue. So for instance here, I can get a solution here now. You see now, I can even take 1. If I put my x as 1, then my y will simply be what? 8. If I put my x as 1 here, 1 times 2 is 2, plus 8 will be 10. Is this not a solution? It's a solution. And I can get other solutions. I can put my x as 2. If I put my x as 2, this guy will reduce. 2 times 2 is 4. What will I add to 4 to give me 10? That's 6. Okay, so this is also a solution. So this has infinitely many solutions. In fact, whenever you give a value to x, you always get a value for y. So it has many solutions. Alright, so that's for the types of solutions. Remember I said we are going to look at the conditions for all of these solutions to happen. Right, so meanwhile, let's now see how to solve equations. So in solving systems of linear equations, one of the major methods we make use of is what we call the Gaussian elimination method. Now there are other methods that we make use of. Now but this is very prominent, and that's what we'll be considering at this point. As we proceed, we are also going to look at other methods of doing this. Alright, now what is the Gaussian elimination method? It has particularly two steps or two things that make up the Gaussian elimination. One is what we call the triangular reduction. Triangular reduction. Okay, so I should be able to do triangular reduction. That is, now you can see what I have here now. This is in a triangular form. Okay, so if you are given a system, you can see this system is in a block form. So if you are given a system and you are required to reduce it to the triangular form, if you reduce it to a triangular form, then you will now apply the second thing, or what I can call the second component, which is what we call the back substitution or backward substitution. Okay, so the Gaussian elimination involves the triangular reduction and the backward substitution. So by the time I have reduced it into a triangular form, then I can now substitute backwardly to get all the values of my variables. Alright, so we are now going to be learning how do we do triangular reduction and how do we do backward substitution. Now look at a nice example here. The example we have here has already done the triangular reduction. So we are going to start with the backward substitution so that you will capture what that one is, and then I will now show you how to do triangular reduction. So what does it mean to do backward substitution? So after you have done your triangular reduction and you have something like this, so this example says we should solve this. So this person has already reduced, and so we only want to do backward substitution. And what is that? You can see why it is called backward is that you can see that the last variable already has a value. So you can see our x3 is equal to 0. Okay, so what do I do next? I will now substitute x3 into equation 2 and then make x2 the subject to get my x2, and then substitute x2 and x3 to now get x1. So that's why we call it backward substitution. So look at that. So since solution now, so I already have that my x3 is equal to 0. So if I now substitute in equation 2, that's going to give me x2 plus, of course, 4 times 0 is 0, and that's equal to 7. Therefore, my x2 alone is equal to 7 because 4 times 0 will go away. And so I have gotten my x3 and my x2. So I will substitute the 2 into equation 1. And that is going to be x1 plus 2 times my x2, which is 7. Then minus 3 times x3, which is 0, equal to 4 now. So of course this guy will go away. So I just have 14 here. That is x1 plus 14 equal to 4. So from there I can easily see if I take this 14 to the other side, I will get my x1 to be 4 minus 14, and that is negative 10. So that's going to give me negative 10. So my x1 is minus 10, my x2 is 7, and my x3 is 0. Therefore, the solution set for this system is simply equal to 0. Okay, let me write it here. So the solution set is my minus 10, 7, 0. So that is the solution. And you can easily see that this satisfies this solution type. So this is a unique solution. There's no other solution, just one. And that is minus 10, 7, and 0. Why did I write it this way? Minus 10 is for x1, and x1 is the first component. The x2 is the second component, and x3 is the last. Okay, so this is what backward substitution is about. So you from here solve backwards. So assuming that this was, let's say, 2x3 equal to 4. So, or let me say equal to 6. So all I need to do here now is I will solve the last equation, and that will give my x3 to be 3, and then I'll substitute here, solve this, and then substitute finally and get my answer. Alright, so this is what backward substitution is. And so in the next video, we are going to be considering the complete Gaussian elimination, triangular reduction, and the backward substitution, and we'll use some examples to see that. Alright, so this is where we end it for this video. Kindly subscribe to my YouTube channel and do give a thumbs up to this video as it helps our algorithm. We'll see you in our next video. Bye. And also, please remember to follow us, join our membership group, and you can also give us super thanks. It will encourage the channel, and we'll of course be able to reach more persons. And so thank you very much. Bye.